Okay, so the next thing we want to consider is the center of a power series. Okay, so let's look at the following example. Consider the function f of x equals 1 over 4 minus x. Say we want a power series representation of f of x. Let's see now that we can actually approach this multiple ways. So here's method 1. This is going to be generally in line with what we've been doing so far. So we read f of x as 1 over 4 minus x. Now we usually want 1 over 1 minus something, so we take out the 4, and we've got 1 over 1 minus x over 4. So we write that as 1 over 4 times the sum from n equals 0 to infinity of x over 4 to the n. And remember, this is only valid as long as x over 4 in absolute value is less than 1. So this, just bringing the quarter in, is going to be sum n equals 0 to infinity 1 over 4 times 1 over 4 to the n times x to the n. And that's equal to, if we multiply the 1 over 4 times the 1 over 4 to the n, we get 1 over 4 to the n plus 1 x to the n. Okay, and just to elaborate more on where this is valid for, x over 4 less than 1 implies that absolute value of x is less than 4, i.e. x can be between minus 4 and 4. Okay, now let's see method 2. Method 2. F of x again is just 1 over 4 minus x. But this time we're going to write it as 1 minus x minus 3 over 1. Now, that's equal to, using exactly the same philosophy as if I had a w, I can plug in whatever I want, is equal to this geometric sum, as long as the absolute value of now x minus 3 has to be less than 1. So this is equal to 1 plus, in the dot 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 notation, x minus 3 plus x minus 3 squared plus dot dot dot. Okay, now let's flesh out where this is valid for. What this means is that the gap between x and 3 has to be less than 1. So if we're at 3, we can only go 1 to the right, which would be 4, and 1 to the left, which would be 2. So that means that x has to be between 2 and 4. Okay. Here we had from minus 4 to 4. Here we have from 2 to 4. So we found two different power series expansions of the same function, but they're valid for different intervals. So remark, the interval, and what do we notice about the difference? What's different about this second type of interval? The interval in method 2 is centered at 3 rather than centered at 0, like all the intervals we've done before this have been. Okay? And this is going to motivate the next definition. Okay, so definition. A power series centered at A is a power series of the form sum Cn x minus a to the n, from n is 0 to infinity. Now expanding this out in the dot 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 notation, this would be c0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed, so on. Okay, where, just to introduce some terminology, a is a constant, x is a variable, cn's, again, are constants called the coefficients of the power series. And A is often referred to as the center. So A is a constant called the center of the power series. Okay, so this is why our previous definition was a power series centered at 0, because we only had x, and that's the same as x minus 0. So this is a power series centered at A. Okay, so remark. One. If we think about this as a function, which we've done before, in exactly the same way, if we plug in a for x, what do we get? We get cn a minus a to the n. Now, if we write that out in the dot 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 notation, that's c naught plus c1 a minus a plus c2 a minus a squared. What do we notice about all these a minus a's? Well, they're all 0. So the only term that survives is going to be c naught. So what have we inferred from this? We can think about the power series centered today as a machine. Now this is very important, NB. A power series centered at A always converges for x equals a. So no matter what the CNs are, you can always plug in a, and this function always makes sense at a. So in particular, power series centered at 0 always converges for x equal to 0. So in any of the power series we've seen before, plug in x equals 0 makes sense when we've expanded it as a power series centered at 0. So anything except method 2 in the last example. So if we are interested in the behavior of a function f near a, okay, so for values of x that are close to a, it can be useful, if possible, because it's not always possible to represent it in an interval, to expand f in a power series centered at a on some interval. Now when I should say you can always expand it on the interval just a, like the 0 width interval, but if you can expand it on a non-zero width interval, then it can be useful, because if you look at the terms, you have your c0 plus, and then you're going to have c1 x minus a. So when x is close to a, those x minus a's are very small. So you can approximate the behavior of your function by taking the first few terms, and we'll see that later on. That's the philosophy.